Hello everyone. Recently I saw a very beautiful lecture by Milnor. Milnor is one of the living legends of topology and geometry and dynamics as well, and many other subjects in mathematics. And he was describing the story of topology and how it all began with the legendary Swiss mathematician Euler in the year 1736. So the story goes like this, that there was a city in Prussia called Königsberg. So maybe I can write the name. Maybe I'm not pronouncing it right. So this is, I saw in Wikipedia, this is known as Kaliningrad in modern Russia. And so in the city of Königsberg, the city map sort of looked like this. So maybe I can draw a picture of that, a rough picture. So this is all water bodies I'm drawing, something like this. And there was this waterlogged land, and then some more water here, and so you can imagine these as rivers maybe. And maybe I can shade the region a little bit to show you where the water exactly is. So, and this is not an exact picture, of course, but sort of looked like that. And then there were bridges in the city. So let me indicate the bridges in red. So there were two bridges like this, two bridges like this, two like that, three like this. Okay. And I can also sort of shade them to show you exactly where the bridges are. There are 7 of them. Now, Euler was presented with this problem that is it possible for a particular person, so maybe I can draw the person like this. So a particular person to start at a particular spot, maybe here, or maybe the person is here, who knows. So one can choose a starting position, but whatever starting position the person chooses, is it possible to make one tour? So make one tour and visit all bridges exactly once. So exactly once, that's the key. So suppose maybe this person is an inspector and we are trying to minimize the amount of path or amount of visits to each bridge to exactly once. So he wants to tour the entire place, but he wants to visit all the bridges exactly once during his tour of inspection. So this is a very plausible problem, and Euler was presented with this question that what kind of path this inspector might choose so that he sort of visits every bridge exactly once, and you are back into this region. Now if you want to go back, you have to sort of use this bridge one more time and then visit the remaining 2. So the city sort of wanted a optimized path so that every bridge can be visited exactly once. This was the problem. Now Euler, being one of the greatest mathematicians of all time, quickly realized that it does not matter how long the bridges are or how these regions look like. So these kind of stuff related to measurement doesn't really matter. What matters is how many regions are here and which region is connected to which region using how many bridges and so on. So in some sense, Euler discovered that to solve this problem, measurement is not important. And that means we are doing something different from geometry. Geometry was up till then the crown jewel of mathematics, and Euler found out that it does not matter how you measure these bridges or this area of these regions. All this stuff is irrelevant. Only the connections or the network sort of mattered. So this was 1736, and there was no graph theory at that time. So he proposed a very novel problem, a novel solution to this. So what he did is he converted each of the regions. So he sort of compressed the information. So let me just remove some of this clutter, and so he sort of compressed this information in a very ingenious manner. So maybe I can just do the same. So what he did is he gave a name to each region. So let's call this region 1, and let's remove this extra lines just to keep it clean. Okay, so he called this region 1, and then this one as region 2, this is region 3, and this is region 4. So notice that there are only 4 regions. So what he did is he put 4 dots for each of these 4 regions. 4 dots for each of these 4 regions. And then he connected the regions. So this is region 1, region 2, region 3, and region 4. So then he connected the regions by an edge, or they connected the dots by an edge if there is a bridge between them. So for example, between region 1 and region 4 there are 2 bridges. So he would draw 2 edges. Similarly, for between region 4 and region 3 there are 2 edges. So he would draw 2 edges like this. And then between region 4 and region 2 there is exactly 1 bridge, which is this one. So there is 1 edge. And between region 1 and region 2 there is 1 edge. And between region 2 and region 3 there is 1 edge. So now the question has been reduced to this picture. So the actual picture doesn't matter, only the connections and the configuration sort of matter. And what do you want to do? Well, you would want to travel along each of these edges. Remember, those were the bridges. So you want to travel along each of these edges in whatever direction is that will make this thing possible, and you want to travel along each edge exactly once. So travel along each edge exactly once. And if you do that, whether it is possible to do that or not. So you want to visit every edge, and you want to visit every edge exactly once, whether it's possible. So we will solve this problem in this particular discussion, because it's a very ingenious and but simple solution, and I'm pretty sure that if you try it on your own you will be able to find the pattern. So here is how you can go about it. Suppose there are k edges in this picture. So I'm doing the most general case, but of course in this particular case you have 1, 2, 3, 4, 5, 6, 7. So there are 7, and so the k is equal to 7 in this particular case, but I'm doing it for the most general case. So suppose there are k edges in this picture, and what you want is you want to visit every edge exactly once. So suppose there is a way of doing that. So maybe the way, so if you do that, there will be a sequence of edges. So E11, E12, E13, E14, like this up to E1k. So this sequence is sort of the map of doing that, of visiting every edge, or rather the route of doing that. So route of visiting every edge exactly once. So you first visit E11, then you visit E12. So from E11 you go to E12, from E12 you go to E13. So these are adjacent edges. So you can do that, and there is some sequence of these edges which works. Suppose that happens. We don't know whether it does, but if it's possible, then there will be a sequence of such edges. And these will be, in this particular case, it will be these 7 edges in some order, right? So that's why I did not write E1, I wrote E11. So E11 could be one of these 7 edges, maybe E6, who knows. Okay, so what we will do is, we will, instead of writing the name of the edges, we will convert them into the edge name of the vertices. So V01, V11, V12, V13, V14, etc. And then you will have V1k. Okay, so now, so what did you do? You basically wrote the name of the vertices instead of the name of the edges. So edge 11 is starting at V01 and going up to V11. Maybe that's the thing. So I'll give you an example to sort of clarify what's going on. So suppose this is the picture. It's a very simple picture, and maybe this one is edge 1, this one is edge 2, this one is edge 3, this one is edge 4, and maybe there is another edge, just to make things a little bit more complicated. So this one is edge 5. So one way to do this, and this might not be the best way of doing it. Maybe there is another edge like this. I'll just add a different edge connecting E1 to E. So this vertex to that. So let me give names to the vertices just for the sake of it. So so A, B, C, D. Okay. So now I want a route that visits every edge exactly once. So maybe my route is like this. I start like this, and then I go like this, and then I go like that, and then I go like this, then I go like this, and I sort of fail because this outer edge is not there. So maybe I can just remove the outer edge once just to make sure that it's happening. Okay, so how did I travel? So what did I do? So I first did E1. So maybe I can write it here. E1. First I did E1, and then I did E2, and then I did E3, then I did E4, and then finally I did E5. So this is a very simple code, and this is the sequence of edges that works. There could be another sequence of edges, but this one definitely works. So what I'll do is I will write down the initial and the terminal vertex of E1. So A, B, then B, C, then C, D, then DA, then AC. So that's how I write this down. Now, remember that this C here is written like this because it is the terminal vertex of E2 and the origin vertex of E3. E2 and E3. So C is here because it qualifies for that. It's the place where E2 ends and it's the place where E3 begins. So how many edges are incident? How many edges are incident on C? So how many edges sort of end up in C? So since C is appearing here, for this appearance, we know there are two of them. One is E2 and one is E3. So just by the fact that C appears here, there are exactly, it sort of records two edges that are incident on C. But see, C also appears here. This is the last edge. So that means one edge is incident on C, and that is recorded by the appearance of C in the last spot. So in total, three edges are incident on C. Are incident on C. So this is known as the degree of C. The degree of C. So every time C appears somewhere in the middle, that gives two edges that are incident on C. That gives two edges that are incident on C. So maybe C again would appear here. I don't know. I mean, for a different graph, for a different set of vertices and edges, for a different network, it might so happen that C again appears somewhere in the middle. So if it did, then this one would also contribute a 2. But if C appears at the beginning or at the end, then that appearance accounts for one edge being incident on C. So every time a vertex is somewhere in between, two edges are getting recorded. That appearance of this vertex tells me there are two edges incident on that vertex. If the same vertex appears once more here, again two edges would be accounted for. But if that vertex appears at the very end or at the very beginning, then that would account for one edge being incident on that vertex. Now that means there are at most two vertices that can have odd number of edges incident on them. However, if the first and the last one are the same, then there are 0 vertices with odd number of edges incident on them. So there are either two vertices with odd number of edges incident on them, or there are exactly 0 vertex. None. If the first and the last one are the same, then there are 0 vertices with odd number of edges incident of them. So this is known as the necessary condition. This might not be sufficient. Well, later someone proved that this is sufficient, but this is for the moment the proof that we provided. This tells you a necessary condition that must be satisfied in order to even hope that this will work. There will be a path like this. So what is the necessary condition? The necessary condition is there are 0 or 2 vertices with odd number of edges incident on them. Is this sufficient? Well, the proof that we provided so far does not say that. It only says that this is necessary. Later, as I said, another mathematician proved that this is sufficient, but for the moment, necessary condition is enough for us to answer Euler's question. Well, you can see easily that there is R2 with 3 edges incident on it, R1 with 3 edges incident on it, and R3 with 3 edges incident on it, and R4 with 5 edges incident on it. So there are, each of these 4 vertices has odd number of edges incident on it, but we know that at most 2 of them are allowed to have that. So clearly it's impossible to have such a path, and this was Euler's proof, and this was sort of the beginning of graph theory as well as topology. Topology because again no geometric information was necessary, and topology is in some sense, topology can be in some sense geometry blind. So it doesn't always, in most cases, in some cases it does not depend on the geometry. You are allowed to stretch or do other stuff to your configuration, and that's sort of the crux of topology. You are allowed to transform your space of work by continuous functions, which has continuous inverses in some sense. Okay, so this was the beginning of topology. I hope you liked it. You can try to prove that this one is sufficient condition for such a path to exist. Such paths are known as Eulerian paths, and they have been extensively studied in graph theory. Okay, thank you for watching.